So I will be talking about weighted blowups, different applications of weighted blowups. Today I will be mostly focused on foliations. And I will be talking about weighted blowups, but from a very particular point of view of torus actions, which actually give us the additional advantage for resolution. So let me say a few words about the nature of weights. If we consider a resolution of singularity, Hironaka resolution of singularities, we see weights already there. They are present in an implicit way as a part of the invariant, especially invariant in so-called ER0. And they have a nice geometric interpretation. They should be understood as the best approximation of the weighted approximation of the variety. But there is some kind of problem with Hironaka approach. It's not a problem, but it gives us some difficulties when we try to extend the method, or we would like to understand maybe method of Hironaka. The problem is that Hironaka used all followers used smooth centers without weights, and they are not quite suitable for resolution of singularities. So we sort of we do not resolve singularities, but we sort of transform them into more toric varieties. So at some point it becomes, the singularity becomes a hybrid of toric and non-toric singularity, which is not so easy to understand. One can understand this in the level of the induction quite easily. The inductive steps are simple, but if you want to write the formulas for the resolution and write the transformation of the singularities describing functions, then we get something very complicated. So what happens is that, for instance, we consider the standard very simple singularity of that form, and we naturally have we can associate weights, and we can naturally associate invariant, which is in this case 2, 3, 4, and this gives us approximation by the weighted cone, and this is the right approximation. But but smooth center ignores this, because smooth centers associate weight 1 to all those coordinates. As a result, our singularity seemingly gets much worse. And to understand it's actually better, it requires to introduce a special logarithmic structure and control. And this logarithmic structure controls the singularity in a complicated way. So for instance, this may be not such a big problem in characteristic 0, but for instance, in positive characteristic, or in the case of foliation, it's a substantial problem. For instance, if we consider foliation, we have to use, for resolution, we have to use weighted blowups. There is no chance, otherwise our singularity will never improve beyond a certain type of singularity. So this is simply a necessary tool. Even in positive characteristic, using weighted center simplifies a lot, and actually it eliminates many difficulties associated, for instance, with logarithmic structure. To begin with, there are famous Moa-Biancar jumping phenomena, and they are non-existing. They are typical typical to smooth center. They do not make any sense for weighted center. For a weighted center, they are not. They not create any problem. And then this very complicated already logarithmic structure in characteristic 0, and then in characteristic P, it becomes practically non-manageable, and we get a very substantial problem for the obstacle for the resolution solved by introducing weighted blowups. And now there are only essential difficulties left, with, for instance, in positive characteristic, and non-essential, which are associated with smoothness, smooth centers will disappear. So, in a sense, smooth centers are not that smooth. They are kind of rough. They are not enough. They are not tangential enough. They are not tangential enough to singularities. Like I said, and they are completely non-manageable in positive characteristics. And in the case of foliation, it's even more clear situation because the other language cannot be used. Let me say a few words about the short history of the resolution by weighted center. In 2019, the paper by McQuillan and at the same time joint paper with Abramovich and Temkin on functorial embedded resolution appear on arXiv. And then sometime later there was a different version which was written in the language of torus action. I'm going to talk. Oh, sorry, not this one. I'm going to talk about torus action today, and you will see. So at the beginning, one could think that maybe presentation by torus action is similar to this given by weighted blowup and by orbifolds, but we already see on the level of foliation that there is a dramatic difference. So formulas, transformation, everything is much simpler in the language of torus action than as versus orbifolds. And today I'm going to talk about foliation, and this is a joint project with Abramovich, Belotto, Temkin on principalization and of logarithmically foliated orbifolds, and also resolution of some types of singularities. In this case, we are talking about, for instance, Darboux singularity or totally integrable singularities. All right, so let me start from recalling what is a foliation. It will be just involutive distribution, so sheaf of logarithmic derivations, which is closed under a Lie bracket. So in the paper with Abramovich, Belotto, and Temkin, we prove the results, which are sort of to some extent continuation to our results on the project of resolution of morphisms. So we have a project on a resolution of morphisms when we prove that every morphism is resolvable by one can transform any let's say dominant morphism by logarithmically smooth morphism, and we use also transformation which are not quite weighted blowup, but some stack theoretic blowups in this approach, and we also need to use orbifolds. But so this is the method which was initiated is sort of extension of the. I mean, this method is sort of extension of the method from the paper on the relative resolution of morphisms, but on the other hand, it is an extension of other papers. So on the paper of resolution by weighted blowups, and most notably the methods used are quite similar as in my paper on torus action. So the method which I used here are the method of Riesz algebras and torus actions. So this is what I'm going to talk about. So first theorem just tells us that I can, it looks like Hironaka theorem, but it just says that it's a foliated version of Hironaka theorem. So it means that I have a sequence of weighted blowups, or cobordant blow-ups. As a matter of fact, I mostly will be talking about cobordant blow-ups. I will give this definition at some point in my talk. And now the goal of, so I have a smooth foliated variety, I have an ideal, and the goal is to principal this principle is to make it, principalize it and make it into monomial. But it's very important here, the difference that centers the Fi align. I will explain what does it mean. So they are well compatible with foliation. And this has some consequences for the resolution of foliations and some others. So there are some other properties. If F is non-singular, then this, for instance, all this transform foliations also singular. So this is more like a technical result, and the other results will be consequences of this result of
principalization. So first result is embedded desingularization. Here we can, given a foliation and a subvariety, I can resolve my subvariety in such a way that resulting subvariety is smooth and is F aligned. So it's sort of decomposed in F transverse and F tangential parts. And all blowups are F aligned. And yes, this process is compatible with smooth morphism. So another version of Hironaka embedded theorem, but this time in the presence of foliation. Now the first application is just about transverse section. So let me tell you briefly what's a transverse section. So we say that subvariety is transverse if the subvariety is described by some set of parameters, and there are some derivations in my foliation which are coming from these parameters. And if the rank is the right one, then we can call it transverse section. So in this case, foliation is described by derivative corresponding to this coordinate. So we get the most natural situation that we have actually a foliation which are transversal everywhere to the section. So this is always, if I have the generically transverse, I can resolve to subvariety, I can resolve it and make it smooth and make it transverse to my foliation. That's a very first consequence of this result. Next is the theorem about the resolution preserving transverse locus. If I have, if I have foliated variety, closed subvariety, I can make it, which is generically transverse, by sequence of I can find an embedded desingularization which makes Y prime smooth and transverse to F prime, where F prime is the strict transform of F. And the sequence is isomorphic over the points where Y was already a transverse. So that's first application. Another application is related to resolution of the foliation. So resolution of the foliation is a very difficult problem. And actually, foliation cannot be resolved. They only can be reduced to a special types. So, but paradoxally, and then even in the simplest situation, let's say you have a foliation X partial X, this kind of foliation cannot be resolved. There's nothing you could do. I mean, you cannot blow up this point, because you get exactly the same foliation. So even the simplest case, you cannot make it into non-singular. But paradoxally, using the cobordant blow-up, one can resolve some classes of totally integrable foliation and Darboux foliation. So this is what I'm going to talk about. So what is totally integrable foliation? So basically, one should think about this foliation, which is as a foliation which is defined by by global meromorphic first integrals. So it means any derivative here is just vanishes on the function coming from the base. There is a morphism x to b coming from the base, and all the pullbacks of the function should be considered as first integrals, and this foliation is defined by first integrals. So by derivation, all the functions which vanish on this pullback. So this is what we called globally rationally totally integrable. And there is another version of of this theorem where we will, I mean, it's not a theorem, it's just a definition. And we also will be talking about the so-called Darboux foliation, but in order to introduce Darboux, we introduce the so-called K-monomial foliation. I guess they were introduced by Belotto, right? So in his paper, it was PhD or something, no? Yeah, yes. So this was introduced and studied by Belotto first, and he actually anticipated that they are related to, they could be like a final form of the foliation, which obtained as a resolution. So resolution of Darboux foliation would give us exactly K-monomial foliation, and this is the best we can expect. Yes. So, and this is in sense it is true, and it was proven locally by Belotto. But in a sense, you will see that if you consider cobordant blow-up, it's even too weak, because actually it turns out that you could make them smooth. Okay, so what is K-monomial? K-monomial is a little bit, I mean, for people not working on foliation, this is a little bit shocking definition. We have a subfield of the base field, and locally our foliation looks like this. So defined by, in a certain system of coordinates, it is defined by partial with respect to V, and also this kind of expression where these coefficients belong to the field. So for instance, very often they belong to Q, and in this case they are called Q monomial. So Q is probably the most common situation, but they may belong to some other fields. So the field, to which it belongs, it matters a lot in this case. And the true meaning of K-monomiality, why they are called monomial? I mean, there's nothing monomial here, but it turns out the idea of monomial foliation is this: just they have monomial first integrals. But these first integrals, these are not ordinary monomials, but they have actually, the exponents are in the field K. So they are sort of symbolic monomials, which could be understood, for instance, in analysis. It could be in analytic geometry, could be understood as multi-variable function. The thing is that maybe these first integrals look strange and look like more formal expressions, but their differential, they look exactly very nice and looks like this. These are differential of monomial function with coefficient with exponents in K. So they look like standard nice forms. And yeah, so these are K-monomial variety. And why I'm introducing K-monomial? Because this leads us to, this is a particular sort of case of K-Darboux function. And K-Darboux means that there exists now, previously we had, again, morphism into B, rational morphism to base B, and we have first integrals given by pullbacks of the function. But now we just assume that foliation F is the pullback of a certain K-monomial foliation on B. And that's what we call K-Darboux, and this is sort of equivalent to local definition of K-Darboux. So it's essentially the same notion, but with but here we use base B, and then both. Yes, sorry. Both kind of foliation could be resolved. First, we can observe easily. It's a very simple lemma that it's easy to resolve a k-monomial foliation and make it smooth. So basically, I can, if I see a foliation like, if I see foliation like this, I can easily resolve it, and the resolution is very simple. We just blow up, use cobordant blow up at the center W. And singularity immediately of foliation immediately improves. So it means that monomial foliation could be resolved. And this is actually a very simple result, but then it's not surprising maybe now that we could totally resolve all Darboux or totally rational integrable foliation. So there exists resolution, non-singular cobordant resolution, so something very unusual for foliation to have non-singular resolution of totally or respectively k-Darboux integrable foliation XFE. So, and then what is the property of this? So the strict transform is non-singular of the foliation. And what is the property of this cobordant blow? It means it is not a birational transformation, but if we look, this X admits a geometric quotient, and we look at the space of orbit, that the corresponding morphism is birational. So it's birational in the sense of quotient by torus action. Yes, and this implies the resolution, so Q monomial. So of course, for orbifolds, we cannot have non-singular resolution, but we have Q monomial or respectively K monomial orbifold resolution of totally integrable foliation. So this we can retrieve this stack theoretic orbifold resolution by taking simply stack theoretic quotient of the cobordant resolution. So they are closely related. It's in a sense, cobordant resolution is easier to handle but contains all the information on the level of two different quotient. On the level of, we can do standard geometric quotient, and we can consider stack theoretic quotient. And the result is just a non-singular monomial foliation on variety with torus action, or here, or in the case of the foliated, it would be the Q monomial or K monomial foliation. So this is indeed what exactly Belotto anticipated, that Q monomial are the right form for the orbifolds resolution of k-Darboux, k-Darboux foliation. So this is the consequence of our theorem. So let me talk about the method of resolution, and these are not only related to resolution of singularities, and both resolution of singularities and resolution of foliation. So what is, let me explain you what is this cobordant resolution and what is the language which is suitable for resolution of varieties. Gives us quite fast resolution of varieties and quite fast resolution of foliation. You see that those languages are nearly identical. It's just similar language, but with added foliation, of course, there are associated difficulties. So let's start from the definition of the order. Order is simply a maximum integer such that E is in the power of the maximal ideal at the point, right? And this definition, we could rewrite it in the language of Riesz algebra. I can consider the following Riesz algebra generated by maximum ideal at the point. And then it would be a maximum point A such that the expression ITA will be inside this Riesz algebra. This is simply rewriting this condition. Now I can rescale this condition and use the language of rational Riesz algebra, so with rational powers, and I could write my order in such a way. Maximum, this would be maximum rational number, which of course is integral, such that IT is in this rational algebra. Why I'm using this translation? Because this is how our and now I'm talking about resolution of singularities first, and then I will show how the same invariant will work in the context of foliation. So we start from order, and we write this order in such a form, and this allows me to think about the definition of invariant, resolution invariant. Here it is, almost identical to order, but instead of MPT to the 1 over A, I have just some kind of now I have a order defined in such a way that we have coordinates with weights. Previously, all weights were equal to 1 or 1 over A, and now because we didn't have weighted center and just smooth center, but this is like approximation of the I at the point P by weighted center. So this is done in the language of rational Riesz algebra. So definition is almost identical. This int stands for integral closure. And the same extends to, I mean, this is a technical maybe, but this extends to any rational Riesz algebra, which is maybe used in the process, because maybe we start from ideal, but in the process it's more convenient to work with Riesz algebras. Rational Riesz algebra. So now what we do with our center for which this we get the invariant. So this invariant is associated with this Riesz algebra, and we could use the sort of trick which was first used by Riesz when he introduced the extended Riesz algebra. So we take this little additional generator, and now things become very simple adding these additional generators. So let me show you. So after rescaling this Riesz algebra, we get the center, and we get what is called full cobordant blow-up. So full cobordant blow-up is defined by just rescaling the condition which is in the rescaling this admissibility condition, which is in the very definition of the center. So look at this very interesting transformation. What is this? It doesn't look like a blow-up at all, because it's an affine. It's an affine transformation. It's an affine transformation. What we get is a scheme or variety which is one-dimensional bigger. We introduce new variable t. So t is no longer dummy variable, but it becomes an essential variable for the resolution. So, and it's actually t inverse represents the exceptional divisor. So it's like OX1 in the third twisting sheaf OX1. So t minus 1 is exactly the generator of the divisor. So, and this is a full cobordant blow-up. This has magnificent properties in terms of the transformation. So suddenly, actually our variety, as I show you in the moment, translates to exactly the same variety. I mean, in the situation. So it's basically describes. We get no improvement in the singularities of this level. But let me just finish the definition. So this is full cobordant blow-up. But in order to see cobordant blow-up, as in the case of blow-up, which is a projection, we have to remove a vertex, and the vertex is defined by the coordinates new coordinates we introduce. Because in our case, we introduce the following coordinates, T inverse, and these are new coordinates which makes our variety smooth. So we see them here. So they are extremely simple. There are extremely simple transformation rule associated with cobordant blowup. And now, if you take the part which are given by sort of transport of the x1, xk, we get so-called the vertex, and indeed, cobordant blowup is just full cobordant blowup with removed vertex. Now this, we also have a trivial cobordant blowup when we remove the exceptional divisor Vt inverse. So let me show you on the picture how the transformation looks like, right? So we are the same. So this is a full cobordant blowup. We have a center. Here we have a torus action here given by T, so it's a canonical torus action. And above the center, we see the vertex part and the cobordant part. So and now in the full cobordant. In the cobordant, we remove vertex. So what happens if I remove vertex? So now I will this way I will discontinue or disconnect all the orbits above the center. So you see this, all those orbits, they are connected, right? So if I remove V, they will create, on the level of the space of orbits, they will create the divisor, right? So the blow-up is just removing vertex. If I remove vertex, I create divisor on the level of the quotient. And so we can analyze, so what is the relation of this construction with the weighted blow-up? So ordinary weighted blow-up is simply geometric quotient. The problem with ordinary, why don't we use just ordinary geometric quotient? Because this geometric quotient is not smooth, and it's very difficult to work with non-smooth ambient varieties. So practically it's very impractical to consider non-singular singular ambient varieties. So but we can also consider stack theoretic quotient by a torus, and then we get a smooth object which is locally described by a variety with a finite group action. And now, yes, this is remarked. The weighted blow-ups were introduced by Macmillan and Marceau and Abramovich, Temkin, Wlodarczyk in this paper, which were from 2019. And cobordant blow-ups were introduced in my paper independently as presentation of weighted blow-ups in a Queck and Reed paper. So next I will show you how this works for, so how the actually resolution looks like. So remember the admissibility condition, which is defined in the definition of the invariant. So we have this admissibility condition. IT lies in this rational Riesz algebra. And I can translate this, rescale it into the condition, on the for the cobordant blowup. So it turns out that this gives us definition of the control transform of I. So control transform of I comes from the admissibility condition. So all just works together. So, but still, I think the invariant of control transform achieves this maximum at the vertex. So after blow-up, vertex becomes the worst locus. And this maximum is exactly the same as along the center. So my situation at the center, at least in characteristic 0, in some cases in positive characteristic. So the situation along the center and the quality of the singular, or the type of singularity of the center is nearly identical as for the control of the singularity of control transform at the vertex. So vertex and center will give us exactly the same singularity. But now, if I remove this part associated with vertex, then of course I improve singularity. So one can say that this resolution is done by removing the worst locus, literally removing them, because transformation of cobordant blow-up is just certain modification. But now after which basically gives us very similar singularities, but removing this bad singularity locus give us the improvement. So for instance, let me show you how it works on this very simple example, this Briskon singularity. And we can, of course, compute its invariant, which is very easy in this language and a very fast process. We get that the invariant is obviously B1, Bn. So this is the powers. The weights will be correspondingly 1 over B1 and 1 over Bn. So after rescaling, the integral weights gives us this kind of expression. And you will see that I get, this is the exceptional divisor now. And the control transform, if I want to compute transform, I just ignore exceptional divisor. And I get exactly the same formula. So I start with this formula, and I get exactly the same formula after full cobordant blow-up. So seemingly nothing changed, but I changed my torus action. And what happened is, to resolve singularity, I just remove the singular point. Just remove it. And we know it's, if I remove it, so there's there's nothing left. There's no singularity anymore. So on the level of cobordant blow-up, I did some kind of trick here, and then I removed singularity. So first, the full cobordant blow-up seemingly does nothing. But the second operation of removing vertex really is the one that removes singularity. Okay, so yeah, so after exactly strict transform is the same, and then when we remove singular locus, of course we are left with no singularity situation. Right. So. Then the process of resolution is just very straightforward. The maximum, so this is a very geometric invariant. So roughly speaking, invariant is associated with the best approximation by weighted tangent cone. And so we have these weights of best approximated weighted tangent cone, and we have a natural weighted center. And after blow up at this weighted center, our invariant drops. So it's very simple geometric process. But it is done, like I said, up to torus action, or up to the on the level of orbifolds. Because we covered this very non-trivial combinatorial part of Hironaka resolution in torus action. It's now hidden, and it is separated from the rest. So geometric part is very clear and straightforward. So what is left is just to handle this combinatorial part afterwards. So one just need to somehow handle the varieties with locally toric singularities, which are done, for instance, in my paper, but it is very straightforward process. It's like a resolution of canonical resolution of toric varieties. There is such a thing which was introduced in my paper, canonical resolution. Okay, so now now let's go back to foliation, because after all, we started from the foliation. I just wanted to show that the method is closely related. Now the invariant is very similar. You remember the invariant was such that we considered some power A1, AK, such that IT was in this part. But now we have to consider also part which is related to foliation. I mean, both parts are related to foliation. One is related to transversal part of the foliation, another to sort of invariant part of the foliation. So, so this is an invariant which is related to foliation and ideal. And we have this, this condition, the same condition as before. But now there is also foliation coming into play. So those conditions x1, those coordinates x1, xk, they should be present in the foliation as the partial derivative with respect to corresponding coordinates. So look, if f is just ordinary sheaf of derivations, then we get the same invariant as before, because clearly, if I have, I don't have any other, I don't need any other coordinates. All my f is just spanned by partial x. So the other part is so-called invariant. So there is a transversal part which is defined by those coordinates x, and there is an invariant part defined by coordinates y, which are f invariant. So f preserves this. So this idea, it comes from, for instance, our paper on resolution of morphism, where we use this f order, but in this case it is relative. Or instead of f, we consider a relative differential sheaf of relative derivations, and we apply this sheaf as long as we can. And if the relative order is infinite, then we have to deal with invariant part, and this is very similar situation. So we can find those coordinates, and if action by f does not produce any coordinates, we just have to deal with invariant part. Okay, and then the situation is very similar. The maximum invariant drops after each blow-up, and the process continues until we reach exactly the same type of invariant 1, 1, 1. But then there is some kind of, the center is, in this case, f align. So it has f transverse part and f tangential. So it's compatible, not only smooth, but it's compatible with foliation. Yes, foliation. Okay, so yes. So now let me show you briefly how the process of resolution of Darboux integrable foliation works, because this was one of the key points of my talk. So one of the application. So let's say we have the morphism B into our base, and our foliation is just pullback of the foliation G, which is either trivial on B, or for totally rational integrable foliation, or G's k-monomial. In such a case, I mean, this is pretty standard graph trick. We just pull back, we consider the product x cross b and the graph inside, which is isomorphic to x. So here I assume that this is a morphism, not a rational morphism for simplicity. And then I could take a pullback from b to y of the function of the foliation g. So it will be k-monomial. And my foliation f, original foliation, is just restriction of some k-monomial foliation to the graph x, right? So now I can apply, for instance, embedded desingularization. If h is, because h is k-monomial, so I could make it into non-singular, as I mentioned in the lemma. And then I can apply embedded desingularization. We know that the process, if I mentioned this, the process will give me, on the level of the y, will give me centers which are h aligned, and h will be always smooth. So no wonder if h is smooth and h aligned, at the end I also have the center which is equal to x, the transform of x, which will be smooth and aligned. But smooth and aligned means exactly that it's non-singular. Because our foliation on ambient variety is non-singular, so align with non-singular center, and the restriction to aligned center gives me a non-singular non-singular foliation. And on the level of orbifolds, it gives me this similar theorem, but as a result, we get a k-monomial foliation. Lastly, I would like to explain the geometry behind this cobordant resolution. So how is it possible that I have singular foliation, x partial x at 0, and how is it possible that I still can resolve it by using cobordant blowup? So it's actually quite nice to see. So this is my vector field, x partial x. This vector field vanishes at 0. And if I lifted this to the cobordant foliation, it basically will be a similar foliation x prime, partial x prime. But now I remove x prime equals 0, locus. So I remove the vertex. And so you see that here, these arrows, these are invariant fields. So of course they are getting longer and longer if you move along the orbits. So if you move along the orbits, you'll see longer and longer the field. So above 0, we get actually those vector field, which is now non-singular. So we lift this singular foliation to a non-singular one, and we see that above 0, we get nice singular variety, nice singular vector field, which collapses to this 0 point, because all this part, exceptional divisor and vertex, they collapse to the center. So this way, it is still possible to resolve singularities by resolve some foliations by non-singular foliation, which is something unheard in the language of foliations, because foliations, they are, like I said, they are unresolvable and nothing could be done. All right, so that's all. Thank you very much.
So in your example, the strict transform was equal to the control transform, but usually you use...
no, this is on the level of derivations. Not so with form. This language. I mean, on the level of differential form, it does not. It looks different. You know, it's not like, you know. So we need to use the language of you know, we think of forms as dual to derivations, simply, you know.
Yeah, but I mean in the previous example without the foliation.
Yes, in the previous example.
Yeah. When you iterate the process, you look at the control transform at each step.
Yes, I use a strict transform.
The strict or the control transform?
Strict transform, or actually, one can also use control transform. You know, so both should work. Strict transform gives us a much faster process, you know. But I think, as far as I remember, the control transform should also work. Should work, yeah. Yeah. Yeah, so it's basically the same as with resolution of singularity. One can use both, and simply it's much faster to use strict transform, because you just factor out as much as you can, versus in control transform you factor what is guaranteed by by the process, you know. So there is a certain because what's the idea of the control transform? Control transform is just, it was introduced by Hironaka, but it looks now slightly a little bit different. It's just we are factoring out, in our case, this is guaranteed that we factor. Oh, not. Oh, this is that we factor this power. This power is guaranteed that we can factor it, because look, this is T inverse is exceptional divisor. So we are dividing here by exceptional divisor, and this already behaves nicely, you know.
if after factoring out the exceptional divisor. But you know, it turns out that sometimes we can actually factor more, right? We can factor because this is what is guaranteed, that that already will be improved, you know. But it turns out that it may be, you know, obviously in some situation maybe that we accumulate a higher power of exceptional divisor, which could be factored out, right? Yeah, so it is exactly, I mean, the original idea goes back to Hironaka. When, if you blow up at smooth center, and your smooth center is inside of the locus where the order is D, that you are guaranteed to factor at least the exceptional divisor to the D power, you know, D power. But sometimes you could factor out much more, or maybe everything even, you know.
Another question? Yeah, if you wait for the
Oh.
So, hello. So first, I would like to make the very biased comment that I thought it was a great talk of my collaborator. And I just wanted to say some words about the perspective also of dynamical system. So because the problem and the question that we're working can be traced in some form to works in the 90s about the Hilbert 16 problem, and especially to works of Denkoska, Husserl, and later about Panazzolo, Pelletier, Brunella. And so some of the notions as Jarek present of this K-monomial or the F-align, they already were hinted in the papers of Denkoska and Husserl. Later they appear in Panazzolo's. I work with them in my thesis, and now we have the weighted case. And in this community also like anticipated that weights were going to be quite important. The example of Sans and Sanchez of Fernando's shows that resolution of foliations is not in general possible without weights. And but somehow the community did not have the foundations and to actually do this. And the work of Abramovich, Temkin, Wlodarczyk, and now also with the Riese algebras and cobordant of Jarek really gives us this tool. And this is maybe the first step in a project that I believe we can revisit a lot of those problems. So I don't know, I just wanted to share my.
Okay.
Your last question or comment? Okay, if not, let's thank first Jarek again.